you. Oh, there it was. It was going. Whatever. Okay. Do this thing. I'm coming. I swear. I didn't forget. Just have all these things to do. Okay. 17, right? So here's the trick. This is something we should be able to do relatively quickly. We know that for the parent function, I'll do it over here. So it's asking to find the vertical asymptotes on 0 to 4 pi for right, Lee? Or tests, right? Okay. So I'm going to explain a little bit about what I'm about to do and why this is going to accomplish what I want, and then I'll actually go talk about, like, okay, so in general, this is all we need to do, but it's maybe not entirely clear, like, what even should you do upon first reading this, so I want to do a little bit of background to kind of flush that out a little bit. So remember, for the parent function, we have a vertical asymptote here at pi over 2, or negative pi over 2, excuse me, again at pi over 2, right? And this is, one period is pi total. Or you could have thought it's equal to pi over 2k, where k is an integer and odd. So that's kind of the same thing. So here for this one, my period is going to change, right? Since b is 1/2. So that means my period is going to be pi over 2. So now I'll have a period, or I'll have my undefined here and over here, right? Where this is pi over 2. So far, so good? So if I want all of my asymptotes on 0 to 4 pi, the first asymptote happens at x equals pi over 4. And the second one then is going to happen pi over 2 further, or 3 pi over 4. And the third one then is going to happen pi over that. So that's going to be 5 pi over 4. The fourth one would happen at pi over 2 after that, 7 pi over 4. And then we'd have another one at 9 pi over 4 and 15 pi over 4. But that's where it ends, because after that you'd get to 17 pi over 4, and that's bigger than 4 pi. So that's our list there. So that's out. In general, though, this is what we did. So if I take any tangent function, kind of in our form of a transformation, our asymptote is going to be at x equals 1/2, oops, I'm sorry, it was pi over 2 times b, probably want to say absolute value of b, yeah, times k, where k is an integer and k is odd. H is going to matter there too, though, right? Yeah. So we should say, let's do this. Try to do it as generally as I can. There. So this is in general. So test then, all we would need to do is just keep picking value of k until we exceeded the upper bound for our solution set, or for the range that we were given. Times. But you kind of see what I did there? So I started with the fundamental, figured out what the new period is, figured out where the new asymptotes would be at, and then just added the period to get my next asymptote as many times as I needed to until I was outside of the range that I was given. So that's the idea. Now, whether you want to do that, I personally would probably do it this way all the time, just because to me, it feels like I'm not going to goof that up. Like I would goof up the formula if I tried to do just the formula. But I won't goof up. I know the key points, so that I can make sure I can transform the first key point and then just add the period a bunch of times. But whatever, that's the idea. Does that feel okay? Okay. That's good for you too? I have a person that sits in front of Tess. I forget. No, I know. Brooke. No, not even close. What's your name? Anna. That was way off. Ludwig. Okay. All right. Do we want to do some more? There are other things from homework you want to look at? Again, they don't have to just be from the last homework assignment. At any point, homeworks is fine to talk about. We're nearing the end of this chapter. So if there's still things that you're catching up on, it's okay to talk about those again. Chris?
Are there
yeah, there are. I'll get them up into the content library here, hopefully today. Is my goal. I have been nonstop doing stuff, but I do have answer keys that I can post. Megan. Yes. Is 18 just that?
Yeah.
Okay. So the only difference here, let me use a different color, is here B would be 2. Are you good with why B is 2?
Yeah.
Okay. So that means that my period is going to go from negative pi to positive pi. That's my asymptotes. So the first one would be at pi, and then I'd add 2 pi to get to 3 pi, and then I'm done. What I did is I transformed the key points from tangent.
Oh, okay.
So I multiplied the x-coordinate by b to get the new location for the asymptote. And because I have both asymptotes, I know the period also doubled. So basically, I just took the first asymptote that was inside of my range at pi, and then added 2 pi to it, my new period, to get 3 pi. And if I add 2 pi again, I'm outside of the range for the problem, so I'm done. So there's just 2 asymptotes. Does that feel okay? Are you sure? Because I hand waved a lot of that.
So you add period?
Yeah. So if you think graph, what's going to happen here, we have some asymptote, and then 1 period later, we'd have next asymptote, right? And then 1 period after that, we'd have another asymptote. You know what I mean?
Yeah.
So if I figure out the location of the first one, I can just keep adding the period, and that'll give me the location of the next asymptote. And I add another period to that one, and I get the next one. And I can just, once I have one of the asymptotes, I can find all the rest of them that I need just by consecutively adding one more period to it. Yeah, or you could just do pi times absolute value of b for a tangent function. You could do that also. Either way of thinking about it is fine.
Okay.
And why do we know that adding one period is going to get us back to the same kind of point again? This is the same idea as coterminal, right? One period is basically going to be one trip around the unit circle, so you're going to end up back at the same location, so the same value point is going to pop up again. Does that make sense? Trying to connect it back to ideas from last chapter, because that is trigonometry. Like, nothing goes away. It all just kind of builds on top of each other, and all these ideas come back over and over and over again. But that's nice, right? Like, if you didn't quite get it the first time, you're going to get a chance to see it again and again and again. But it makes it important that, like, you really learn it, but, you know, like, try to learn it the first time through, because it never really goes away, you know. The cram and then forget is a bad strategy in this class. You know what I mean? Like, there's classes where that's okay, right? Where you cram for one chapter and the next chapter is wholly unrelated to it. You know, like what you learned about in Huck Finn doesn't really help you when you're reading the Scarlet Letter or something like that, where you can just kind of like cram for the book. But when it comes to like writing, like what you learned about writing in one chapter matters in the next chapter, right? Because writing is writing. You know what I mean? So this is a content where it pays to not forget. Anyways, that's enough of that. I didn't mean to harp on English. It was just an easy example, because obviously two books are not, they have nothing to do with one another, is an easy example. Okay. We feel okay about the homeworks? We'll take any last questions if you guys got them, but if you don't, we can move on. There's not a lot left in chapter 3 to do, which is okay, right? You guys are probably good with having a short day today. I'm certainly okay with it. I'm poo-poo tired. But if you guys have anything more, we'll just kind of get started and get this day done with. You know what I mean? In the words of Larry the Cable Guy, let's get her done. That may be a reference that's too old for any of you. No? Nobody gets that? God, I'm old. All right. So the last section in chapter 3 is about harmonic motion. And basically what we're talking about are real life scenarios that we can model using a trigonometric function, like a sinusoidal function. Okay? So one of the most common examples would be if you're talking about like a Ferris wheel, like something that's spinning. So whether you're talking about, like I use a Ferris wheel a lot because it's something that I think most students have had some visual reference to, so it's easy for you to visualize. But like, if you're interested in cars, most of the parts on cars are spinning. Same kind of thing. You could model like the drive shaft spinning with a sinusoidal function. But that's a thing that if you're not familiar with cars doesn't really help you out any. So I try to stay away from those that having no background reference for kind of makes it a little harder. You know what I mean? But if you're a car dude, like there's lots of, car engineering parts that are spinning that are certainly all good candidates to represent with a sinusoidal function. We'll do some examples where we involve some Ferris wheels, mostly because it's something that at least I think everybody's seen like it on television if you haven't ridden a Ferris wheel. Right, you get the idea of what it looks like and what it does. And I am just like kind of tapping my feet here because I don't want to write down the entire text for these story problems. So I'm trying to pull up my Word copy of the book so I can copy and paste it in. But my computer's being unbelievably slow right now. So it's like just dragging along. So this is me kind of tapping my feet and doing a little dance while I'm trying to open this file on my computer. So that's the reason why we're stalled here. Not that what I'm talking about is at all important, but it's just me trying to fill the silence so it doesn't feel so awkward. But now that I've acknowledged it, it maybe makes it more awkward. I don't know. I'm not sure. What do you guys think? More awkward? Maybe we're moving past the awkward part to where now it's starting to get funny. Is it getting funny? I don't know. And you guys are all wearing masks, so I can't see if you're smiling at this. As I continue to ramble on for no real apparent reason, other than being uncomfortable with sitting in silence and having you guys wonder what the heck is he doing over here. So I'm just kind of narrating the process of what I'm doing. But I'm getting very close to actually having what I'm looking for so that I can copy and paste it in here and we can get going on this. But not yet. So, and now I finally run out of things to say. Silence. Now it's awkward. Unbelievable how slow the computer gets by the end of the day for me. I mean, I have a lot of stuff running, but it is rough sometimes. I mean, I guess I like having the laptop or whatever, but boy, I would like to have a real, like a powerful desktop computer to have at work instead of the tablet. Like I use the heck out of that feature, but it's not a very powerful machine. And that's a little frustrating for me. You know. All right. Yeah, good. All right. Finally, it's here. So let's do an example. So the idea here is we're going to write a sinusoidal function, like a sine or cosine function, to describe the behavior for this Ferris wheel. So it says a 100-foot diameter Ferris wheel is positioned with the center of the Ferris wheel 55 feet off the ground. The Ferris wheel spins at a rate of 1 revolution per 2 minutes. Construct a function to model the height of a rider, where the height is measured in feet and time in seconds. And the rider enters the Ferris wheel at its lowest position. Okay, so I'm going to sketch a little picture of kind of what's going on. So let's say there's my Ferris wheel. Everybody okay with that? Looks kind of Ferris wheely. So it says at its lowest point, it is 55 feet off the ground. And we're told the diameter is 1 feet. So let's include a disclaimer for all the people that are very picky out there. I'll just write not to scale here because clearly 55 is not half the length of the 100 that I drew there, but you know, who really cares? They're just labels. Everybody's okay with that so far? Okay. So it says that we want this function to model the height of the rider. So that should be the y-coordinate. And time then would be the x-coordinate. So I'm going to kind of stumble my way through this first one intentionally as I kind of talk through how I'm able to determine like what information I can use for what. But I want to kind of justify it with a common sense argument. And then as we go further, I'll streamline this process a little bit and talk about like, okay, this information always gives me this, rather than starting with that fact because I know it already, but you guys don't. So it'll be a little bit of a, you know, like pretend discovery process. Megan, you're ready to ask a question already. Go ahead.
Why would the 55 feel below the 57?
Oh, good call. So good. So what should that be? Yeah. And now it looks much more to scale, right? Maybe I'll just erase that. So I don't know, the center-ish. Oops. Center-ish was what? Right about here, maybe? Thank you. Good point. I'm glad you saved me from that embarrassment. Reading comprehension pays off, guys. Okay. So, it says that the rider enters the Ferris wheel at its lowest position. So that's going to be time 0. And the height there would be well, it's 5 feet off the ground still, right? This is the lowest position. Is everybody okay there? That's what our... And is that going to be... What kind of value is that? Is that a minimum, maximum, midline value? This is a minimum for our function, right? Everybody agree with that? Okay. And then we know we're doing 1 revolution every 2 minutes. So 120 seconds later, actually, let's do that. Leave some space there. We're back at the minimum again. Everybody agree with that? What is this telling me? Yeah, what's the period? Yeah, 2 minutes or 120 seconds, right? Everybody agree with that? So I can use that then to sort out my value for B. And this is a point that I want to make here. I can't remember. I think it was in both classes. I saw lots of people in the homework quiz when we're solving for B doing this wrong. So if I divide both sides by 2 pi, let's write it out. That gives me 120 over 2 pi, right? If I reduce that, that becomes 60 over 60 pi. I saw lots of people dividing by pi and then somehow the pi becomes in the numerator instead of staying in the denominator. So I just wanted to kind of refresh our algebra there a little bit because it happened a lot. So I must have screwed that up at some point or not made that clear enough. But I'm trying to do that right now. So just be careful when you're doing that. So our B value then is either positive or negative 60 over pi. Is everybody okay there? Good. At what time would this Ferris wheel reach its maximum? 60, right? Halfway in between. And what would that maximum height be? Would be what? 105, right? Everybody okay there? When is it going to be at a midline point? At 30. Everybody agree with that? Okay. And what would that midline point value be? 55. Is everybody okay with why that's 55? Basically, we're here, right? Which again is the same as the 55. Okay. So let's fill in some values. Now that we have all these points, it should be really clear what some of these values are, right? What's my value for K? 55, right? The y coordinate from the midline point. And what's my value for A? 50 or negative 50, right? Everybody okay there? And then H depends on whether I want to make a sine or a cosine function, right? So depending on which one I choose, H will depend on that. So let's do that. If it were you, which one would you use, sine or cosine? Does it really matter in this case? After we've come up with midline points and maxes and mins and all that, I don't think it really matters, right? Now, in general, I would probably not go and generate all these points, and I would just use this as a cosine function. The reason being, the piece of information we knew right away in the beginning was a minimum. Everything else we had to kind of like reason out a little bit. Is that okay? But it doesn't matter at this point, so let's do it for both. So if we're going to do this as a sine function, let's do that one. Actually, let's do the cosine function first. Why not? So what's a answer for the cosine function? So what would the h be? Or a possible h? There's lots of them. Anybody want to venture? It's okay to be wrong and just take a guess, if you remember, ish. So the parent function for cosine is 0, 1, and that's at a maximum. So what kind of point would we want to be looking at? The maxes or mins, right? So a possible h value could be or 60 or 120. Any of those could be appropriate h's. In mind, if we picked h to be 0, what else would we have to make sure we use? A negative value for a. If we picked 60, we'd have to have a positive value for a. Or if we picked 120, we'd need a negative value for a. Delaney? Okay. So the way we know that is we're going maximum to minimum. So that meant the a would be negative. Same thing here. I'd be going maximum to minimum so that we know the a would be negative. But if we went max to max, there we know the a should need to be positive. Does that feel okay? So let's just say, for the sake of argument, we did this one. So we have y equals negative 50 cosine of, the reciprocal. So, well, I'll write it as 1 over 60 over pi, x minus 0 plus 55. Is everybody okay with that answer? Okay. Let's do the same answer using sine, just to demonstrate that we can. Does it matter on a test or quiz which one you use? Not unless I tell you specifically do this, unless the directions say, but if there's no direction specifying which one to do, you're free to use either. So remember, we're going to use 0, 0, which was our midline point. And remember that the order, we had minimum, midline point, and then maximum in the parent function. So here, what would our h value be? Good. 30 or 90. Great. And if we picked 30, does the a have to be positive or negative? If I look at 30 here, from minimum to midline point to maximum, so that should be positive. But if we look at 90, we go maximum, midline, minimum. With that one, the a should be negative. Either would be fine to use, though. For the sake of argument, let's use this one. Everybody okay with what we did there? Okay, so let's clean this up and talk about what information from the story problem we can translate immediately into terms of A, B, H's, and K's, so we don't have to do like quite this much work. But I think this was probably really helpful and informative to help develop like why these relationships we're about to outline exist. Right? So I don't want to start with just a shortcut. Let's talk through, and then we can turn it into a shortcut. Okay. The magnitude is basically the radius, right? K, the height to the center. The period is the time for one rotation. And I would say the h is related to the starting position, depending on whether you're using sine or cosine. But the h is basically the time unit for the starting position. Assuming that I didn't give you something cuckoo crazy like it's starting at like a 45-degree angle with the ground or something. I wouldn't do that. Does that help kind of hopefully speed things up the next go around? I don't want these to take a million years to where you have to like kind of figure it out, right?
What does it say?
It says related to starting position. So like our Ferris wheel started here, and that 0 became the h when we used the cosine function because it was at a minimum. Oh, sorry, time of one rotation. I misunderstood.
No, you're not.
Or I just wasn't listening. I have a headache. It's the end of the day. I'm really tired. What does it say after what? height to center. You're welcome. You can tell it's getting to the end of the day and I'm tired because my penmanship is also starting to go, apparently. Let's do another example now that we've kind of streamlined that process a little bit. Sound okay to you guys? And this is really all I want to do for the rest of today is we're just going to do a couple of examples. We're going to be done. Sound okay to you guys? I hope so. Hope nobody's like, no, I want to do more. It's like, oh, okay. You can if you want to. On a topic of my choosing, because I don't have anything else prepared related to this topic, but, you know. Okay, yes. Sure. All right. So the next example says, use function from the previous example, find the height of the rider after he has been on the Ferris wheel for 73 seconds. And part B says a woman's height is 40 off the ground. How long may she have been on the Ferris wheel for? So let's pick one of the functions that we wrote to use for this problem. I'm going to use my answer for the cosine. And I'm actually going to write it instead. Remember we said the y was height, so I'm going to call the YH. And the x coordinate we said was time, so I'm going to call XT. And I'm going to clean it up a little bit so it doesn't look quite so weird. So I did some simplifying there too. So there's our answer from the previous example. How do I find the height after we've been on the Ferris wheel for 73 seconds? Ben? Easier than that. Megan? Yeah, we're just going to put 73 in for t. Now, when we do this, it's an important point. We're using sine or cosine on our calculator. What mode does our calculator need to be in? It needs to be in radians. How do I know that it needs to be in radians? Because when we found our period, we called it 2 pi b, 360 b. So we got to make sure that our calculator is radian mode. But that's it. So let's call the calculator here. Bring, bring. Calculator, are you home? Apparently it's not answering. Is my calculator giving me a busy signal? You gonna send me to voicemail? I mean, legit. Like, are we not giving? All right, I'll just use the one. I won't show it on apparently because it wants to be difficult. That's fine. It's a difficult day. Checking to make sure I'm in radian mode. Everybody remembers how to do that, right? If you don't, let me know. So when I type this in, I get, it's rounded to 2 decimal places, 86 feet. Does that seem like a reasonable answer? Let's go back and look at some of the analysis that we did before. So after 73 seconds, we're going to be somewhere over here, right? Do we have a number that's between 55 and 105? Yep. Should it be closer to, which one should it be closer to, the 105 or the 55? Well, 73 is closer to 60 than it is to 90, right? So it should be closer to 105 than it is to 55, which is, again, what we saw. Who's pretty convinced that we have the right answer? I would be. This seems pretty reasonable. But it's easy to make thinking about the physical problem and making sure does your answer make sense? Is a good way to kind of check your work. If you had used degree mode, you would have gotten a cuckoo crazy answer here that would have made very. Everybody good with that? Let's do part B. So it says the woman is 45 feet off the ground. How long may she have been on the Ferris wheel for? How am I going to solve that? What quantity am I looking for? Okay, hold on a second. What quantity are we looking for? A time, right? It says how long may she have been on the Ferris wheel? That's a time question, right? Okay, so we're solving for t. What are we going to plug in for h? 45. Okay, so this is the equation we're going to solve. What do you want to do first to solve this equation? Subtract 55. Very good. And then what? Divide by negative 50. Okay, now what? What do we have to get rid of next? If we're trying to solve for t. Okay, so we have to get the cosine function first. But cosine isn't a number, it's an operation. So we can't, it'd be like saying, oh, I'm going to divide by square root symbol. So what operation cancels out a cosine? This is a geometry question. Yeah, cosine inverse or inverse cosine, yeah. So that's what we're going to do to both sides. Is everybody okay there? And now you could type that into your calculator right now, but you're going to get a cuckoo crazy answer for cosine inverse. So I'm just going to leave it there for a minute, and I'm going to type it in all at once at the end. But you can do whatever you'd like. If you want now, right now is fine. But I don't want to write down the decimal a bunch of times. Is everybody okay with that? Okay. And then last step then would be to multiply by 60 over pi, right? Oops. So I have 60 over pi times cosine inverse 1 over 5 is equal to t. Now it's calculator time. So let's type that in. Oh, it did finally open. Look at that. Just took a million years. Well, maybe next time I need to use you, I'll use you. Okay. Can I ask a follow-up question to this? Did you find the wording for part B a little strange? The wording for question B? Specifically, it said how long May should have been on the Ferris wheel. Do we know that she was on for 26.15 seconds? No, why not? Megan? Yeah, so this could be her second trip around. So this could be also, really we have 26.15 plus 120k seconds. Everybody agree with that? Is there another place on the first rotation that the height would have also been at 45? Let's go back and look at our picture. Oh boy, we're getting laggy. Okay, come on now. So 45 would be around here, correct? So this would have been like our 26, 45 that we're seeing. This also would be at something, 40. Does everybody agree with that? So how would we find this other one if just for, for grins in case if we were interested? Well, here's what we would do. We're going to go back to the unit circle. Everybody agree? Remember where cosine is positive. It's positive in the first quadrant. In the third quadrant. I'm sorry, fourth quadrant. Everybody agree with that? So this angle here and this with respect to the x-axis are the same measurement. Everybody agree with that? You remember that from chapter 2? That was one of our key observations that we made. Allowed us to translate between right triangle definition and angle of rotation definition. So this measure then would be 120 minus 26.5. Right? One full rotation of our Ferris wheel is 120 seconds. That's like here to here. But we need to take back that 26.15. So the completest possible answer are these. So 26, for any angle coterminal to 26, or really we should say time, these are times, and then 93.85, or any time coterminal to 93.85. We'll do more of that in later chapters where we focus on solving. I would not expect you to give me both answers in that complete of a form on a test or quiz. If you gave me the 26.15, I would have been happy. Everybody okay there? But I figure if we're going to do it, let's do it right. Like give me the most complete answer possible. Considering that we have the tools that we needed to be able to figure out, the most complete version of that. It says at 8:15 a.m., high tide comes in on Siesta Key in Florida, and the depth of the water is 18.3 feet. At 11:27 a.m., the depth of the water at low tide is 11.8 feet. Model the depth of the water using a sinusoidal function. Find the depth of the water at 8 p.m. And then find when will the first high tide occur the following day. So I would start by kind of drawing a picture so I get a good feel of the situation. So like we have our high tide here. This is at 5:15 a.m. at 18.3 feet. Everybody okay there? And then later on we have at 11:27 a.m. we have a low tide at 11.8 feet. Everybody agree with that? So that's the information that we know. What can we do with this information? Dan? Yeah, it's like our max and min. We should do something, though, with the x-coordinate, though, because the x-coordinate is written in, like, hours and minutes, right? Everybody agree with that? Let's convert this into, like, hours on a military scale, like a military time scale. Everybody, do we know what military time is? So military time is like a 0 to 23 hour scale. So like 1 a.m. is 1, 2 a.m. is 1, etc. 12 a.m. is 12, 1 p.m. is 13, 2 p.m. is 14, etc. all the way to 12 p.m. is back to 0 again. Everybody okay with that? All right. So 5:15 a.m. becomes 5.25. And 11:27 a.m., 27 divided by 60 is 45, so that's 11.45. Is everybody okay there? So I just converted 15 minutes into a quarter of an hour and 27 minutes into 0.45 of an hour. Okay, so how would I find, say, the K? I would take the X. How would I find the amplitude? That's going to be the midpoint between the maximum and minimum values. How can I figure out the period? So that's one period, right? I extend my graph there a little bit. So how much do I know? That's half of a period, right? From max to min. You guys agree with that? So I know that minus 525 is equal to half a period. So that's 6.2 is equal to 1/2 2 pi times the absolute value. So I have 6 over pi is equal to the absolute value of b. Is everybody okay there? The last thing we'll do is figure out whether we want to use a sine or cosine function, and then the sign on a and the value for h. Given the information that I have, which one would you prefer, sine or cosine? I would use cosine as well because we're given maxes and mins, right? Okay. If we're using a cosine function, which point do you want to use, the maximum or the minimum? Doesn't really matter, but for the sake of argument, let's choose the maximum. So we're going to take the maximum for cosine, take it to the maximum in my transformed function. So my h is 5.25, and my a has to be positive. So I can say, well, not to be confused with that h, I'll write it as h of t for height, is equal to 3.25 cosine of the reciprocal of b times x minus h plus, there's my part A. It asks for the depth of the water at 8 p.m. 8 p.m. is really 20, well, let's say t equals 20. Everybody agree with that? That's me just converting 8 p.m. to military time. So h gives me everybody okay there? And then part C says, when will the first high tide occur the following day? So that is the equivalent of, I want the first maximum after t equals 24. Everybody okay with that? I note that since a half a period is 6-point period would be 12.4. So I have a maximum at 5.25. My next maximum would be at 5.25 plus 1 period, or 1765. This is less than 24, so this is still day 1. My next maximum would occur at 17.5 plus 12.4, which is 30.05. That's greater than 24, so that's now on the second day. So I just now need to convert this into a time. So 30.05 minus 24 is at 6.05. So that's 6 hours and 0. So 6:12 a.m. Is that okay? I had to do some crummy unit conversions there, going from time in hours and seconds, or hours and minutes and hours, into like just hours and then back into minutes and hours so I could get a time. But is that okay with how I kind of reasoned through that? Okay. Well, that's it for chapter 3. We'll have the chapter 3 review. We'll work on that and just take general questions on Monday, and then maybe try to take the chapter 3 test on Thursday next week. If that's an issue, we can talk about it on Monday, and I'm okay with like pushing it back another class period and just starting chapter 4 or something. That's okay to do too. But let's not worry about that until Monday. Okay? So I'm done. Pete? Nope. Dan?
So there's no review.
I'll give that to you guys on Monday and let you work on it on Monday. Yes, so the homework set is just adding these 4 problems, trying to keep your 4-day weekend restful without adding a bunch of other stuff to do. Mango?
So for Sunday, we should have activity 30 on the Thursday.
Yes. No new worksheets. Just those 15 or 16 problems. I guess I'd have to count. I think 16, right, if we go 15 to 30. So hopefully that feels restful after maybe last weekend was kind of hectic. Pedro. Of course. So I'm intentionally not giving you the review yet to force you to do some other work or get some rest or something this long weekend. You know what I mean? It's for your own good. Of course.